Welcome guys to my channel, The Electrocoder, where electricity meets code. Today we are going to dive into a new project that we are going to make. Our project title is Digital Counter. So now guys, let's start the connection for this digital counter project. So guys, I will explain the stepwise connection for this project. Here we are going to make a mode 10 counter. Simply, it is a synchronous counter that will count from 0 to 9. For our counter circuit, we have used 4 JK flip-flops. Flip-flops are simply a memory device that is used to store a single state of binary bit that is either 0 or 1. Here we are going to make a synchronous digital counter. Synchronous means that we are going to supply our clock, that is our control signal, parallelly to all the 4 flip-flops at once. Here we have the clock circuit ready, as you can see in this given figure. We have used a clock pulse of amplitude 1 and period of 1 second with duty cycle 50%. Here the duty cycle of 50% means that the clock is high for 0.5 second and low for the other half. Here for our clock we have used positive edge triggering mechanism, that is our JK flip-flops will be operated at the positive edge of each clock pulse. Now let's understand this clock circuit. For our positive edge triggering mechanism, we have supplied our clock pulse directly as an input for our AND gate, and we have supplied our negation input for another terminal of the AND gate. The AND gate used in Simulink is ideal, but in practical there is some delay between the input and output of the AND gate. So to see that delay, we are using the memory block of Simulink. The sole purpose of this memory block is to simulate a real-world or practical AND gate. Point to be noted is that if we do not supply this memory block, then in AND gate it will create an infinite loop which can cause error in our simulation. Here we can observe that on the rising end of the clock on the upper part of the graph, we can observe a high signal at the lower part. Thus, we have obtained the positive edge triggering. We must use a triggering mechanism for our clock because we are using JK flip-flop. If the duration of our clock pulse is greater than the delay of the circuit, that is, the memory block used, it will create a racing condition. Let's not dive deep into the concept of racing, but we can understand it that if this clock pulse cycle is greater than the delay, then our output will be taken as the input for a short period of time by the circuit, due to which it can create an indeterminate case. Now let's proceed into further connection. Our digital clock circuit is almost going to be completed. Here we can see that we have provided input for our JK flip-flops. As said earlier, our digital counter is a synchronous, that is parallel circuit. That means our clock signal we have obtained is parallelly passed to all the signals at once, as you can see. For the first flip-flop, we have provided a high logic. Here we cannot directly supply 1 to our JK terminal because our JK is a sequential circuit, so we need a Boolean value. Boolean value for simplicity is just a logic high or logic low value, and for 1 we have declared it as logic high as we are using positive logic system. For the second flip-flop, our input is simply Q1. Here Q1, Q2, Q3 and Q4 are the outputs of JK flip-flops respectively. Our Q4 is the MSB for our digital counter, while Q1 acts as the LSB. LSB stands for least significant bit and MSB stands for most significant bit. Similarly, the circuit is connected as shown for the other flip-flops. Till now, our digital counter is counting successfully, but it is counting in binary, that is 0 or 1. This binary system is not user-friendly, that is, the user cannot understand it properly. So, by using this MSB, LSB and other binary bits from the output terminal of JK flip-flop, we are going to combine it to form a decimal number. For that, we are going to use a MATLAB function block. Now let's get into the connection and algorithms used for this. Here we have written this short code in our MATLAB function block. This code simply converts a number in binary system to the number in decimal system. Here U1 acts as the LSB while U4 acts as the MSB. Till now, after we run our simulation, then the final part of the simulation is only shown, that is the end result is only shown. But for counting operation, we need to see the whole simulation, that is counting from 0 to 9 and onwards. For that, we are going to use a block known as a zero order hold. In this zero order hold, we are decreasing the sample time due to which we can observe the simulation going on. Also, the quick summary of the MATLAB function block. I have already said the code we have written in this MATLAB function block. Now, we are just supplying our LSB and MSB sequence to the input terminal of the MATLAB function block. It is very important to maintain the sequence of our binary bit. As you can see, here U1 is the LSB, so we have connected Q1, and U4 is the MSB, so we have connected Q4. Now guys, we have already applied our zero order hold in this circuit. So after we will run our simulation, then we can see our counting operation going on. We will just focus at this part of the code because this is the part where actual counting happens, where our counter generating the binary equivalent bits is converted into a decimal number as shown. So let's start the simulation. Here, after we start our simulation, then our counting operation will be started. Here, the right side of our screen is the binary equivalent, while the left side is the decimal equivalent. Here, we have represented zeros and 1 with the logics in the right hand side, as you can see. So guys, up till this point, our digital counter is counting from 0 to 15. That is, we have made a mode 16 counter, but we are going to make a decade counter, that is a mode 10 counter, that is going to count from 0 to 9. For that, we need to modify our JK flip-flops. That is, we are going to apply the concept of decoding gates in this circuit. Our Simulink doesn't directly provide us with this feature of decoding gates in our JK flip-flop. So we are going to make a subsystem and modify our JK flip-flop. The further connection of this project will be shown in the next part of the video, so let's get connected to it. So guys, this was the first part of our digital counter project. We are going to meet at the second part of the video. Let's get connected for it. This was the electrocoder. Thank you.